Okay, thank you, everybody. Today I'm going to talk about my experience running a set of code that I wrote to be optimal on supercomputers. I noticed my camera's not on. Do you want my camera on? Oh, here we go. There we go. Okay, so let's get started here. So the sort of you might think of an overarching question that I'm trying to answer in this talk I'm giving here is, what are best practices for running massively parallel research/NWP simulations on modern supercomputers? But I'm mostly specifically looking at what are best practices for saving data and saving data frequently. My research workflow involves doing a lot of post hoc, meaning after the model is run, the traditional manner of doing research on supercomputers where you save your data sets and analyze them later. But I need to save data very frequently because it's the nature of the work that I do. So the assumptions going into this whole process that I came up with are: one, the data that I'm saving will be analyzed for years, even for simulation that only takes, say, days to maybe a week on a supercomputer. The second assumption is that the post-processing in the visualization will require a lot less resources, hardware resources, than it took to run the model. So in other words, the data is everything. The idea is to get it saved, compressed, tagged with as much metadata as possible, and in a format that's easy to read and do analysis with. And that's what LOFS turned out to be. So my research is in high resolution cloud modeling. I simulate thunderstorms at resolutions that are at LES, large eddy simulation resolutions on the order of 10 meters or so. My largest simulation is about 250 billion grid zones. I'll show you a little bit from that. I do this because I need to resolve things that are very small and that are moving very quickly because they involve tornadoes. So I'm simulating the violent tornadoes that occur in supercell thunderstorms. So data must be saved frequently because my analysis process involves going through that data and tracing the error through the simulation. This is after it's run. We're doing this from history file data and trying to tell a story here. Also, lots of visualization, which is a surprisingly, maybe not surprisingly, but a very effective method of showing what's going on in these simulations. I don't need to save the full domain data at this kind of frequency, like 5 hertz or so. Mostly I do that kind of saving only in the vicinity of where the tornado is. So I'll do a little animation here. I don't know how it'll turn out over Zoom. I'll pause it a little bit, but you can see this is the vorticity field in a developing tornado. You can see
Lee,
the path. Yes.
Sorry to interrupt you. We're just seeing your title slide right now. So there may be a screen sharing setting that you need to adjust.
Yes, there must be, and I will fix it. Sorry about that. Yeah, that would be, your screen is sharing. I'm going to stop it and restart it.
Yep, we can see it now. Thank you. Or we could.
Is this, so you're, you can see it now?
No, now we just see your camera.
Okay. Now do you see something?
Yes, thank you.
Does it look like a tornado?
Yes.
Okay, all right. And is it moving?
It is, but it just shrunk on your screen again. It seems like
okay. All right, I'm not going to full screen it on my side then. So is it stopping and starting again?
Yep, that's perfect now. Okay. Thank you.
We'll just leave it like this. Apologies for that. So the idea is, as you can see in these animations, that things are moving very quickly. This is data saved every 0.2 of a second. So very frequent saves. And I need that data on disk so I can send error parcels through it so I can make things like this and count the vortices, that sort of thing. So I want to make a distinction here about what's called in situ analysis versus post hoc analysis. In some cases, there's a growing movement, especially with very large simulations, to do what's called in situ visualization. And in situ visualization is when you do your visualization and analysis, say, while the simulation is actually in the memory of the supercomputer. And the limitations of this are that you basically need the entire supercomputer to do this kind of analysis in real time. So you may have to get out of bed at 3 in the morning, to do that. My approach here is pretty much the polar opposite of that, namely that the idea is to get the simulation done, save as much data as you can, and worry about the analysis later. So this is what I'm calling post hoc analysis. And I look at it somewhat like a storm chase. Since I'm looking at tornadoes, you only get one chance to chase a specific storm, because if you miss it, it's gone. these simulations, I've been on supercomputers for a long time, and they can be really hard to get these things across the finish line. There's all sorts of errors that can occur, especially when you're running on the full machine. So my approach here is to just save the data and get it backed up and then work on the analysis later. And in our case, as I said earlier, visualization and analysis requires much more modest hardware than is required for the original simulation. And that's not going to be true for everyone's case. Some people might need to save the data frequently over the full domain, and my approach is still very effective for that because it uses lossy floating point data compression I'll talk about in a minute. So the model I'm using is CM1. It's a cloud model developed at NCAR. It's written to do highly idealized thunderstorm simulations, and it's written in Fortran. It uses OpenMP to do processing on a shared memory node, but also uses MPI. And George wrote it to do non-blocking MPI, so that can overlap communication and computation pretty effectively. This model's been in development for say 15 to 20 years or so. I've been using it for about 10 of those years. So there's different ways to map the machine to the hardware. And one of the things I did was to basically map it in a way that it optimizes the IO process. I'll talk about just in a little bit. By default, there's only one communicator, MPI COM world. I create a new communicator and align it on the hardware in a more optimal way. So the default options for CM1 just don't scale well for very large core counts. So I had to come up with a method to do so that I could do the research I wanted to, which involves saving data very frequently as the model time step, the long time step for the model, which in some cases is a sixth of a second. I've saved a large 20 minutes of model time step data to do trajectory analysis. So I came up with this approach. Basically, I tried lots of different things. I tried parallel NetCDF, parallel HDF, different ways of doing it. I ended up using HDF, something called the core driver in HDF, which allows you to write files to memory. So I'm using serial HDF. I want to be clear about this. So I'm running on these machines that have, MPIs going, you got OpenMP going, but when it comes to IO, I'm just one node is writing one file, but I'm doing all the data collection on a node, and it's all being collected to that one guy who's going to write the file and collect it and buffer it in memory, and then ultimately flush it to disk later. But it's all done with serial MPI. So I've tried serial HDF. I've tried parallel HDF and parallel NetCDF, and I won't go into it, but this method just works better, and it's much more predictable how it's going to happen. So I'm buffering maybe 50 to 100 times into memory before I flush the disk. So traditionally, you save history file data in a model, you save one time per file. I'm saving 50 to 100 times per file for like doing a lot of IO. That means I have fewer files, and the files are bigger. And then when they come out of the memory to disk, they write very quickly on a supercomputer. I wouldn't be able to really do this if I wasn't using compression, and I'm using lossy floating point compression. I'm wondering, maybe someone else who's watching this talk, if they could comment if they've ever used a lossy floating point compression. I'm kind of an evangelist when it comes to it. I think almost all of the scientists should be using it. I'll talk about the compression ratios in a minute. And if you're looking for something to compare this LOFS approach, ZAR is probably the closest thing that I'm aware of, splitting up files basically in an intelligent way. So my strategy is to compress as much data as possible and only save what I need. And what I mean by that is another traditional approach for modeling is to do a bunch of diagnostic calculations and write them off to disk. That just means you have more data to save. And I'm taking the save as little data as possible as frequently as possible. So what I do is we've taken all of the post processing stuff and pulled it out of the model and stuffed it into some code that runs on GPUs and is much faster. So we do almost all of our analysis is done post hoc. And I'll show an example of that in a moment. So diagnostic calculations, they could be written right out, but I typically calculate them after the fact just by saving, say, the components of the wind and the pressure and the basic things you need to calculate other meteorological variables. Multi-core architectures are used for diagnostic calculations. They parallelize easily with OpenMP. It's trivial. You just, whatever loops you're doing over, you just parallelize them. So that's really good. And the entire approach here is to get data saved to disk and then do all your analysis afterwards. And also, when you're saving data frequently, you don't need to save the whole domain, then don't. And that's something else that's configurable at runtime with the model. So I mentioned earlier domain decompositions in MPI. So here is an example of on Frontera, the supercomputer I'm running on right now at TAC. Let's say we've got 4 nodes, just to keep it simple. Now, Frontera nodes actually contain 56 processing cores, but we're going to pretend there's 8, and we're going to have 7 open MP threads for each for each threaded looping section. So CM1 parallelizes the triply nested loops that are updating the model state throughout the simulation. So there's lots of those. But we can pretend there's 8 from the perspective of MPI. So if you just map this, if you just submit the job and it maps it by default in what's called SMP mode, where the first node gets the first 8 ranks, the next node gets the next 8, et cetera. But I'm remapping it so it looks like it's mapped to the hardware, where you could actually like draw a weather map on that second grid and it would map the hardware. The reason I do that is then when I collect the data to that one node, it contains a contiguous volume of atmosphere and I save it to disk. It just makes things a lot easier to deal with. So it also makes the communication pattern as optimal as you can get, as far as I can tell. So one writer on each of these re-ranked nodes is going to handle all of the IO, but it's also going to do computation. So this is not dedicated IO. One core, just when it's time to do data, it says, okay, give me your data, I'm assembling it. And it's pretty fast because you're doing this all in memory primarily, except when you're actually saving to disk, but it's very fast. So the fact that it's not dedicated IO is fine by me. So this all works by using, standards. I have metadata embedded in the file names. I know this is not that uncommon of a practice. That I know satellite data and stuff comes like this, but I basically just came up with a way to label the files and extract metadata from the files so that when I read from one of these directory structures, I can just assemble everything, find a file, pick out metadata, and do all that fun stuff. But you can see I have a base name for a simulation. Then I have a 0 padded time floating point. I'm saving data as frequently as 1/10 of a second or something, 1/7 of a second. So I need some floating point information in there. And I let the sort of least significant digit slop kind of hang around. I worry about that later as well. And finally, I only store 1,000 files per directory as a maximum. It's an arbitrary number. I could set it to whatever I wanted. So the node number is also, when I have a lot of cores, a lot of ranks, you'll make multiple directories and with only 1,000 files maximum per directory. Now, so why do I use ZFP? Because I get really nice compression ratios. Here's an example. Some of the variables I'm getting easily 20 to 1, 50 to 1, 100 to 1. This is shown a box and whiskers plot as a percentage of uncompressed. So remember, it only goes up to 60%. So the worst case scenario, I'm getting about a 2 to 1 compression ratio. Now, the way that ZFP works is you basically tell it what the accuracy that you require is, and it will compress accordingly. So if you look at the far right column with the worst compression, I saved W, the vertical component of the wind, at like 0.1 millimeters per second accuracy. I don't probably need that much accuracy, but it shows you that you still get some pretty good compression ratios. And these are spread apart all the different files. I'm just giving you the ratios for all the files. In regions where things aren't changing too much, your compression tends to do better. If you look at the cloud field, QC, for instance, you notice that the compression ratios, you're only about like at 1% of the full domain because there's a lot of places where there's no cloud. So anyway, ZFP is wonderful. Here's an example of just mapping it out in that 2D domain composition and looking what the compression ratios are for vorticity at 0.1 inverse seconds. So typical compression ratios in this domain are 100 to 1, 600 to 1. Now look in that boxed in area, that's where the interesting data is. And that's the data that I want to be looking at. And then you get more realistic compression ratios because that's where you have strong gradients where the tornado is and things like that. But you're still getting 30 to 1, 15 to 1. And I'm pushing it a little bit with 0.1 inverse seconds, but that's perfectly good for visualization and some simple analysis. You have the choice. You have to choose ahead of time though. You can't get your precision back after you save the data. You take a look at the internal structure of any one of my, LOFS is just HDF files, just named in a certain way with certain metadata and directories. It just looks like this. This is just a tiny segment of the top level, just using H5LS. This one has 27 time slices in it. And I also have soft links that are of a time and floating point. I don't really use those. There's a base state group, a grid group, a mesh group, and a whole bunch of 3D data and stuff that you don't see because it's in the time groups that are 0 padded. So looking in a little bit more, again, I'm only showing you a tiny little bit so it'll fit on the screen okay. You've got 2D fields that are static, some that are statistical. You've got 3D fields, you've got, and then you go to the next time, there's a whole bunch more. There's the base state, all this metadata that any one HDF5 file can basically reconstruct the way the data was laid out. So there's also redundant metadata. The vast majority of the file space is in 3D data. So who cares if each file has identical stuff in it? So there's a bunch of simple metadata, makes it really easy to reconstruct. And as long as you know the LOFS format, it's easy to read the data back. And I have a routine, some routines for that and a pretty simple API as well. So my typical research workflow, I'm trying to simulate individual storms. I have to get the environment I want to simulate in. I'll do some low resolution simulations first to get a feel for how the storm is going, what the motion is. You have to subtract off so it doesn't leave the box. It's kind of the way the thunderstorm models work. You move with the storm. Then once I'm happy with my parameters, I'll submit a high resolution job, an ensemble, a sweep through different parameters, because these storms are very sensitive to parameters and initial conditions. And I'll save checkpoint files, say every 5 minutes or so, but I'll only save data every 10, 100 seconds or every minute. The reason I do this is because I'm going to only go back and do really big saves for the second round from checkpoint files if there's anything interesting. There's a lot of simulations that go on that I'm not going to analyze anymore, but I want to maybe pick a few and then go back and then go and save my data. So there's a sort of a workflow that I do, and I'll show you this and how quick it is and how I can do it all on the supercomputer. So this is a nameless input file for the CM1 model that I've also has my modified stuff in it, and it's kind of split on the screen. I just want to point out a few things. So for this particular simulation, we're running on 2048 MPI ranks. There's the grid domain, 2240 by 2240 by 380. That's 120 kilometers by 120 kilometers by 20 kilometers using a stretched grid. Relatively big simulation. It's a couple of billion grid points, saving data every 1 second. So I'm going back to checkpoint files. I found an interesting segment of the storm. I want to now save data every 1 second to do visualization and maybe some trajectory work. I'm not going to save the full domain though, because I don't need to. I don't need to know what's going on at the boundaries every second. So I only save data. I give the range in X and Y points with respect to what you see with NX and NY. And in this case, I'm saving the full vertical extent to the top of the domain. And here buffering 50 times to memory. So I only hit the file system every 50th write, and then it goes down to the disk. And ZFP accuracy values. So this is where you have to tell ZFP how much accuracy you need. And this is only a tiny snapshot. There's many different choices, and those choices will definitely affect your compression ratios. Now, the tool that I've spent most of my work on is to simply create NetCDF files from the LOFS format. The reason being is NetCDF is like universal. Everything can read NetCDF. Generally speaking, I mean, I've done big NetCDF files that are the size of the domain. It just works. But you can also just use the API and read the data directly from LOFS. I did a recent code refactor that makes that really simple. And in fact, there's some trajectory code that my graduate student, Kelton Halbert, is working on that goes back and hits the API. Doesn't have to go through the intermediate step of making NetCDF files. But they're great for Viz. They're great for all sorts of things. So I have a command line LOFS to NC. I still call it HDF to NC because I only called it LOFS recently. You'll see me when I show the example. But it can, it's pretty flexible. You can basically create just 2D swath files that were saved in the 3D just to get a look at the file. You can create 3D files or 3D fields that are the functions of other fields by doing diagnostic calculations, et cetera, et cetera. You can have it do all the variables, et cetera. So I'm just going to kind of go through an example here. So here I am on Frontera a few days ago. I'm in a directory that has 5 runs in it, and you can see the symbolic links are where the output data is. So I'm going to go CD to one of these directories. Notice the use of base names that are redundant everywhere. You'll see there's a history dot file name, there's or base name, there's all these different things. So within the history data, there's 3D data. Within the 3D file, there's a bunch of directories. And within one of those 3D files, you can see that the actual HDF files, once you get past this, which is the node directory, then you get into the HDF files. And there they are. So there's the data. What I want to do now is actually take a quick look at one of the simulations, look at what are called swath files. So I have a command line for that. I point it at the top level 3D directory. Everything inside that directory, LOFS knows how to read. I'm going to do swaths. I'm going to turn verbosity on so you can see what's going on. I have to pick a time and let it go. This went pretty fast because I had just read this file before, so it's still cached in memory, but I want to show you that in the center of the screen with all those dots, that's when it's actually calculating the metadata or the cache data and getting all the information from the files. And when you see those alphabet soup, the Y's and the Z's, that's when it's actually reading data from the files. And if it's a A, it's reading a small amount. If it's a Z, it's reading the full domain that I'm asking for, the 2-dimensional space. It's just a little silly thing I put there to keep an eye on things. So there's the NetCDF file. So let's take a look at it. So what I'm going to do at this point, I wanted to show you there's the cache file, and there's a couple files in there. I'll show you those right now. And they're just text. And if they're there, it never has to go and do that again. And sometimes it takes a long time to do the caching. It didn't in this case because it was already buffered. So I'm going to sort of helicopter in a VNC because the only reason I use the terminal there is because the fonts are nice. But here we go. I'm going to use NC View. I use this all the time. I'm on the supercomputer right now using a VNC. By the way, VNCs are also wonderful things, and we should all be using them if we're not. I'm sitting on my Charter network. It's not super fast, but it's almost as if I'm sitting in front of the monitor. And this enables me to get a lot of work done. What am I doing here? Well, I'm looking at the reflectivity field, but I'm also picking out a subdomain to create some 3D files for. So I want to go in. If you notice that there's the time index or the spatial indices on the panel will show you where you are in the file. So here I am choosing X not X1, Y not Y1, Y not data. And now I'm reading the 3D data. And you'll notice it's a little slower now. And now you see the letters of the alphabet going by a bit slower. And you'll notice the Z's are always in the middle because you're reading the full, and the stuff on the border is you're only reading chunks of the adjacent file. So it's reading from the file mesh, all using HDF commands. This is all written in C, basically. It's calculating things as it needs to, and it's also just writing them. If it's just transferring it from LOFS to NetC, it just dumps it. It doesn't have to do any calculation. So you see a little bit of calculation, a little bit of just writing. Now we have a subcube file, which is a little bit bigger. Now we'll take a look at that reflectivity field again, but you'll notice I don't have to zoom in this time because I'm only looking at that subset. And now I'll look at the three-dimensional reflectivity field. And I'll start out at the ground. The two-dimensional field was about a half a kilometer up. And there's actually some interesting things going on here. This is actually research in progress. Those stripy looking things are very interesting. They're little tubes of vorticity. You're seeing some interesting things going on in the boundary layer, right? That's being sort of sucked into the tornado. That's where you can sort of see where the tornado is. So anyway, I don't want to get too far, but this is my workflow, and this works really well. I create NetCDF files. Here I'll look at the cloud a little bit, and I can do all sorts of fun stuff. And then all this stuff can be scripted out so I can batch it. The fact that it's only serial HDF shouldn't concern you because I'm always doing like 5,000 times, right? So you just parallelize in time. It's a embarrassingly parallel, and you just make all your files or do all your analysis in parallel. Everything, I'm all about whatever I can do in parallel, I'm doing it in parallel. I can't give talks in parallel. I know that. Anyway, all the mic code, if you're interested or sadistic enough to want to look at it, it's not too bad. It works, and a lot of years of development, it's gotten a lot better. I've brought it up to speed on different versions of the CM1 model because George releases model versions when he does, and I have to adapt my code, but I made it very modular. So you can go to GitHub, that's the Fortran side, and then the read side, which is the code that you just saw me run, is also available. So as I sort of wrap things up here, let's just say on supercomputers, IO can kill you. And if you're on a supercomputer, you're probably doing some grand challenge type problem. And many of those grand challenge type problems require lots of IO. And this is one of them. Okay, tornadoes move fast, and I got to analyze them, and I got to save a lot of data. So this all just kind of came about wanting to do that, needing to do that. I'm an atmospheric scientist. I'm not a computer scientist. So a lot of it might have gone a little slower than if I had had some, formal training on some of these things, but it works. It works. There's another tool out there called Damaris that I would say is similar and better, but it does dedicated IO. And at the time I was considering this whole process, it was just a little too green for me to use. So I use this instead. When it comes to ZFP and floating point compression, lossy floating point compression is where it's at. I think the problems are getting big enough. You don't necessarily need 32 or 64 bits of precision. ZFP, and there's other compression algorithms out there that are similar, allow a scientist to pick that range, pick what they need, and it will compress accordingly. Dealing head on with IO has now allowed me to do amazing things. That you can look at my videos and stuff. It's this approach led to science that is now things that are being discovered in the real world that were found in models. So that's kind of gratifying and cool. So just to wrap up, there's some things the software is always in progress. I'd like to be able to save ZFP encrypted, or not encrypted, but compressed NetCDF files. I have to figure that out. Get all my metadata finalized, do more diagnostic calculations, write a Python driver so we can import it, and exploit new HDF options. And with that, I will put my acknowledgement slide and pause for any questions.